So yeah, today I just kind of wanted to go over kind of the outline of the class. So I'll have these lecture notes and I'll put them on the website later. And yeah, so the way I kind of made this set of kind of this class anyway was I went through all of they have a list of prelim exams, and I went through and just did all of them. And so I tried to organize all of them by kind of category. So they're generally just, there's only about 8 categories of things. And even the eighth one's not super focused on. Um, and so what I would do is somehow these lecture notes are what you kind of need to know, at least definition wise and theorem wise, to pass the exam. But it doesn't give you kind of the flavor of like actually how to do the proofs. It's just kind of all the building blocks you need. So this is not supposed to be a class which, if you haven't seen real analysis, you're supposed to know everything at the beginning. It's supposed to be more of a refresher. So yeah, let's dive into it. So first we'll be talking about measure theory in general. And this is a big chunk of kind of the problems I've seen over the years for this exam. And generally it's just how do we measure sets? What's the different definitions of measurability? How do I define like outer measures and things, properties of weak convergence of measures and stuff like that. And so I'll talk about this today. And next, like later on, we'll talk about measurable functions. In particular, there's theorems called Egorov's theorem and Lucen's theorem, which tell you kind of families of measurable functions, so things which are measurable with respect to the Lebesgue measure, they're almost like continuous functions. So you can remove a small measure set and get a continuous function. And if you have a uniformly bounded family of measurable functions, they converge uniformly up to a small measure set. So the way I think about this is they're like almost continuous. They respect all of that stuff. And then the big part of the exam, I would say, is mostly focused on the next 2 sections. So there's going to be a integration, which is just how do I define integrals? How do I think about integrals? And in particular, when do limits and integrals commute? So I have a sequence of functions and I take its integral. When can I say that the integral of the limit equals the limit of the integrals? So this falls under kind of the names of bounded convergence theorem, dominated convergence theorem, these types of convergence theorems. For the next one, it's studying properties of what are called LP spaces. So just to recall, I have this kind of norm for 1 less than or equal to p less than or equal to infinity, which is just going to be the integral of f to the p, right? And then I have a normalization of 1 over p. And so these spaces are very nice. They have duality properties for p strictly less than 1 and infinity. You can use lots of things about them, and they're generally used in PDEs to get you more information about the PDEs. After that, we'll talk a little bit about Fubini's theorem. So when I have, for example, things like f of x, y, dx, dy, so double integrals, when can I think about it like this? So if I integrate in dx first, it should be the same when I integrate in dy first and then dx. Right? And so Fubini's theorem tells you, okay, when does this make sense? When does this equality make sense? And when is it false? Okay, so that's Fubini's theorem. It's just a version of the statement. The next is Lebesgue differentiation theorem, which we'll talk about later, which is on understanding what happens when I take what I think of as local averages of functions. So the way I think about it is, let's say I have a graph of a function, and I want to look at some ball, and I want to take the average of my function, right? So this is kind of like the average of my function on the ball. So that's equal to this. And the thing about L1 functions, so things which are integrable, are when I do this and I take the limit as the ball b goes to 0, so the limit as b goes to 0, this guy converges to whatever the value at the center point is. So here it'd be something here. right? So I'm taking, if I take smaller and smaller averages, I converge to the actual pointwise evaluation of the function. Okay, so that's the big differentiation. The next kind of, they're more niche topics, but they're still something that is covered in these exams and generally in real analysis classes, is what's called absolute continuity. And so absolute continuity, there's two kind of different definitions of it. One's on the level of functions. And what it basically says is, when is the fundamental theorem of calculus valid? So when can I write f prime of x dx over some interval like x naught, x1? When can I have this equality? x1 minus x2, f of x2, x naught. So functions which are absolutely continuous are exactly the ones which satisfy this fundamental theorem of calculus. So they're continuous. They kind of have derivatives almost everywhere, and I can make sense of this. There's another corresponding notion for measures, which gives you the same thing by what's called the Radon-Nikodym theorem. So we'll talk a little bit about different notions of absolute continuity. And then finally, if we'll have time, it'll be, there's some questions in functional analysis, which if you've seen functional analysis, I think they're fairly basic, but they still might come up. It's less likely though in the exams. Okay, does anybody have any questions about how we're gonna go through this at the moment? Okay, sounds good. Well, let's go right into it. So let's start with measure theory, and I'll post these notes later today on the website. Okay, so the way we start with measure theory is the whole idea is, how do I measure, like, let's say regions of the plane. So let's say I have like some set A that's pretty wild in R2. How do I assign volume to this thing, or a measure to this thing? And naively, what you might think is, okay, I take any subset of the plane. So that's what this means, 2 to the x. So if x is a set, 2 to the x is going to be all of the subsets of x, right? So it's a set of subsets. So it's all collections of sets like A. And it should be a positive thing. So a measure is something that takes in, so an outer measure is something that takes in a set in X, subset of X, spits out a positive number, and it's what's called countably subadditive, and it assigns 0 to the empty set. So what countably subadditive means, let me zoom in here, is the following. So if I have a set A, let me just fix this a little bit. So if I have AK, and I take the union of them, so if I have sets AK, and I look at the union, K goes from 1 to infinity, so it's a countable collection of sets, and then I measure mu of it, I want to have that this is less than or equal to the sum of K equals 1 to infinity. Right, so this is what countable subadditivity means. It's kind of an intuitive notion that you would want for a measure, right? Because if you think about it, like if the AKs are overlapping, say I have, this is a A1, for example, and then I have another set like A2. It's A2, right? So the union is going to be this whole collection of things, right? So if I think about this here, and this less than or equal to is because I'm somehow overcounting this region, right? So if I measure each of these individually, I'll be double counting this intersection. Okay, so that's why that inequality makes sense. Okay, so that's the definition of an outer measure. That's where we start with. Using this concept, we can define the Lebesgue measure, although we haven't defined what a measure is yet. So the idea is, if I'm actually a subset of the plane, I know how to measure really basic things. In particular, I know how to measure cubes, right? So what you can think of, this, let's say I have a set E. So I have some set E here. And I want to figure out how how to approximate its volume. What you can do is you can slowly start covering it by cubes, right? And I'll just do this. And I look at all possible countable covers of the set E. So this is this condition. And then what I do is I take the smallest possible cover of these cubes. So I look at the smallest volume. So in some sense, the outer measure, this Lebesgue measure, is measuring, okay, if you give me any kind of set, what's the best I can approximate it by from above by cubes? Okay. And actually, Lebesgue measure is a example of an actual measure. So there's a distinction between outer measure and measure by restricting the domain of your function. So instead of going from the whole power set, so measuring everything, every subset of X, I restrict to what's called a sigma algebra of my set. Does everybody know what a sigma algebra is? Okay. I can, yeah. So basically it means the following. So a sigma algebra satisfies if I have a countable collection of things. This should imply that one, every complement is within the set. So you give me a collection of things which I think are measurable. I should be able to measure the complement of the set. That should be a thing that's also measurable. And I should be able to measure all unions of sets of countable collections of sets. So these are both in F. This is a sigma algebra. The reason it's called a sigma algebra is somehow the algebraic operation is union and complement. So complement's kind of like minus. And the sigma just means countable. So it's closed under countably doing unions and complements, is all that means. Okay, so let's go back to the definition 3. If X is a set and I look at a sigma algebra, a function mu from this set of subsets, is a measure if it's actually countably additive. So up here, I had countably subadditive. Here, I require it to be countably additive. Okay. And the actual elements of my set, E and F, are what are called the measurable sets. Okay. So what I mean by countable additivity is the following. Just right here. I just mean when I take the measure of a union of AK that are disjoint. So when I write a union with a dot, that means that if I take any two, like an A1 and an A2, and I intersect them, then the intersection's empty, right? So I don't have overlaps like this. So if I do that, I should actually recover the sum. Goes from 1 to infinity of mu of AK. Okay. Can anybody tell me why, like if you've seen this before, this story before, why I'm making a distinction between like an outer measure and a measure? Does anybody intuitively have an understanding for why I need to restrict to this script F?
I mean, you have things, well, gosh, I can't remember the name. The decomposition of a sphere into a bunch of smaller pieces or a
That one's
bunch of
called
paradoxes.
yeah, it's called the Banach-Tarski. So Tarski paradox. Have people heard of this before? Like this kind of paradox? Okay. Yeah, so it ends up being provable that if I'm allowed to measure every subset of, for example, R, by what's called the axiom of choice, I can construct things which I cannot assign a measure to in a way that I would want, right? So a lot of people, there's a couple different ways you can deal with this. One is you reject the axiom of choice and say every single subset of the plane or R I can measure. But that's kind of an uncommon thing. You have to work in a weird axiom system. So what ends up being more common is I restrict myself to only viewing things which are measurable. And for all intents and purposes, that's way more than enough most of the time. Okay. Okay. So let me just talk a little bit more about measurability since that's kind of a big thing. There's this one thing called Carathéodory's theorem, which tells you if you give me an outer measure, how can I find the set of measurable things? So you give me some outer measure of all subsets of, let's say, R. How can I figure out which subsets are actually measurable? Preserve this condition of countable additivity. The answer is by what's called this condition. I call it like a splitting condition. So what it is, step by step, is something is measurable. So if something is in this F, so E is in F, if for every single subset of X, I can split it across its intersection with the set I'm considering and the intersection of the complement. So the way I think you should view this is, let's say you give me some kind of crazy set, right? It's like some blobs. So these are, this is my set A. And I have another set E, which I'm trying to check if it's measurable. And let's say I subset it like this. So this is E. This is E, and then the rest is E complement, right? The idea is I should be able to use my set E to split apart the intersection between A and E and the intersection of A and E complement, right? And so if this happens for every possible collection A, I split my measure like this. Then I say it's measurable, right? And so this is not easy to check that this gives you actually a measure. That's why it's called this Carathéodory's theorem. This was about, I think, 1900s, around 1900s. This was proved, maybe 1920s. Okay. So yeah, it's just kind of nice to keep this in mind. If you give me an outer measure, then I can construct a sigma algebra, which makes it a measure. Okay. In terms of actual examples, you can apply this concept of measurability to figure out what the measurable sets with respect to the Lebesgue measure are. And so there's this fundamental theorem. You can find it, for example, in, I use Whedon and Zygmunt. Textbook on real analysis. So there's a proof. I'm not going to go through the proof here, but I just want to say this condition like you saw from Carathéodory's theorem that for all A, I split across E, right? So for each E in RD, either I split across all sets, or I have this topological condition, which says for every epsilon positive, I can find an open set containing A such that the measure of the difference is small. So what this last condition says is, let's say you give me some set A. And what I want to do is I want to find let's do this, some open set. So this is my O, such that this region in the middle is small. So I want mu of whatever this region is to be less than epsilon. Right? So I can kind of surround my set A by something that's open. Okay, so in general, Lebesgue measurable things are somehow related to open sets. For example, using this definition of Lebesgue measurability, you can check that, okay, every open set is measurable. Can anyone see how that's just assuming theorem two, right? It's going to be zero always. So if it's an open set to begin with, then I can figure it out. Also, I just realized there's a typo. I will fix this. For each A, there exists an open set. I'm calling it E. My apologies. So E is the thing I'm trying to figure out as measurable. Okay. All right, let's go. What time is it? Oh, perfect. Okay. Let's do this. So have you guys, has anyone looked at the handout I sent or the little exercise I sent? If not, that's okay. But I think it would be nice to do it here. So let's figure out how to actually measure things. So I have a measure. I know how all I have are the measure of the empty set is 0, and it's countably additive across disjoint things. So one natural thing that I can do is I can take an increasing sequence of sets and then look at their union, right? So the picture I have in my head is this is A1, A2, and then it keeps going to this is A star, right? Is the union of all of these. What I want to say is that mu of this guy is going to be mu, the limit as k goes to infinity of mu of ak, right? That's a pretty natural notion. If I'm increasing, right, I want the measure to be the limit of each of the individual pieces. Okay. Can anybody tell me why A star is measurable, right? Is anybody?
I mean, it's just part of the definition of a sigma algebra.
Yes. Okay. So that we're good on. Sigma algebras are closed under unions, and they're closed under countable unions. So I know that this guy is good. I can measure this guy. What else? How would you actually prove this? Does anybody have any suggestions?
You can just take the differences of the successive sets, and then you get a disjoint union.
So let's try that. And go and add a page. So no, that's a great idea. So let's call it, what do you want to call it? Like B? Sorry, are you saying something like I let BK be the difference? AK minus 1?
Yeah, and then it's helpful to define A0 to be the empty set so that B1 is defined.
Let's do that. Let's do that. Okay. Then what would you do? So what I've done is I've broken it into pieces. Like I have one piece here, then I have the next piece, then yeah, I have this piece. Right, so I've broken them into rings somehow. Okay, and so the measure, so each of these BKs are disjoint, right? Just by, so BK disjoint. Okay, and so what that means is I can take mu of the union of BKs. And what is the union of BKs, by the way?
A star.
Yes. This is A star, right? Because what I'm doing is I'm starting with this set and then looking at, okay, the next one up, and I just add it, right? And then I keep going all the way up to A star. So this whole thing is still A star. I've just rewritten it a different way. And I know from the fact that these are all disjoint that this is just going to be the sum, mu of BK. Okay. What now?
Yeah, then you rewrite the sum as a limit of the partial sums.
Okay, let's try that. So just to check, mu of bk is mu of ak, ak minus 1. It's going to be mu of ak minus mu of ak minus 1. Okay, so there's one thing you should be aware of when you're doing this kind of thing. I'm allowed to work with, so I have no other conditions about this, right? This is what you were saying to do, right? I need to
Yeah,
measure, I've created this thing, I want to check that these are like this.
well, it isn't what I was saying to do, but it was what I would
Okay,
have eventually done. So yeah, it makes more sense to do it in your order.
okay. Well, one of the things I just realized about this is this quantity may be infinite. So when you're doing this type of thing, um, mu may have infinite values. So we just have to double check sometimes that this makes sense. So for example, if this one's infinity, right? And this one's infinity, I get infinity and minus infinity. So it doesn't quite make sense. But I'd still like to say something. Okay.
In that case, the union is going to be infinite measure. So like if there exists one AK that has infinite measure, then also
There we go.
union has infinite measure, and then the equality is true.
Yes.
So we can assume that does not.
Perfect. So as an aside, you'll see this a lot. This is great. Aside, if mu of AK is equal to infinity for some k, then mu of a star is infinity, right? Because it can only get bigger because, I'm only increasing more things. So without loss of generality, mu of AK is finite for all k. So you'll see this a lot of sometimes I get some weird situations where, oh, maybe I've run into something where I'm looking at two infinities. But then all that usually means is I need to go back to the original problem, look at what I'm actually doing, and check that infinities aren't a problem for me. Okay, so we're here. I can safely forget about thinking about infinities. And what I get in the sum, if I call this star, so star implies, so what did I have? I had mu of a star is equal to the sum, k equals 1 to infinity, of mu of bk, which is equal to the sum, k equals 1 to infinity, of mu of ak minus mu of ak minus 1. Okay. Now, should I be worried about convergence of the series?
No,
Or why not?
because you can use the telescoping series theorem regardless of whether the series converges.
So my issue is sometimes I'm thinking of if I just have this as a AK and AK equals like, let's say plus or minus 1 or negative 1 to the K, right? Just in general. Negative 1 to the K. I can't actually make sense of this sum. Can anybody
Right.
tell me why it's still okay to do this for this thing?
Because it's always non-negative in this case.
Okay, great. Yeah. That's what I'm looking for. So just because, so when I write this, when I go back and look at this, right? I know actually that measures are always positive. So I know that at least we're working with positive measures. So I always know that this guy is greater than or equal to 0. And that's kind of, yeah, that is actually fairly important. Because sometimes if I have this infinite series, sometimes I don't know what to do. If you're working with signed measures, this becomes an issue. Okay, so what I can do now is you write this as the limit as n goes to infinity, right? By definition of a kind of infinite series. AK minus mu of AK minus 1. But I noticed that it telescopes, right? When I go from k equals 1, so this is a of 0, which is 0, and then minus a of 1, plus, and then I get a minus a of 1, and then a2. So in general, this is the limit as n goes to infinity of mu of an, right? All I get is the last one, right? Because everything telescopes. And that actually completes our theorem, our measuring theorem. So we're good there. Okay. Any questions about this general game plan? Okay, great. So I'll let you guys think about what happens for this case when I'm a decreasing sequence of sets. There is this one condition. So if I'm decreasing and I try and look at the smallest one, so the intersection of all of them, I would like to say the same property that mu of the smallest one is the limit of all of the mu's. However, I also need this condition of finiteness. Can anybody tell me why when I have the following? So when does mu of a star not equal the limit of mu of ak?
You can have sets of infinite measure that intersect to nothing. Like if you take the real line, then you just move the interval to, just take an infinite interval and shift it to the right, I guess.
So you're thinking of, I go and I look at the real line, so this is R. And then what is it? I take an interval?
You take
And
an infinite interval from
infinite.
0 to infinity, and then you take 1 to infinity, 2 to infinity.
Yes, okay. So let's say this is k equals 1, right? Is the one that goes from here to here, here to here. And then the next one is k equals 2, right? And that goes from here all the way to infinity. So in general, if I have AK, or I should call it AK, if AK is equal to k infinity, and I'm looking at Lebesgue measure, then what is the limit? So A star is what?
Empty set, she said.
Okay. So if it's the empty set, then actually each of the measures mu of AK is infinity for each of these, right? Because the measure of this interval is just the interval. So this guy is equal to infinity. So the limits can't be equal. 1, 0. So the left-hand side is 0, and the right-hand side is always infinity. So I actually do crucially need this condition of finiteness in order to take limits. Okay. Wonderful. So we've got about a little bit of time. There's another very nice theorem out there involving what are called lim sups and lim imps of sets. So it'd be nice for you to remember what's called the Borel-Cantelli lemma. So what it says is if I look at this lim sup of sets AK, this is still measurable because I'm just taking countable unions and intersections. And I know something about the measure of each of the AKs. So I know that each of these is finite. Then I have that the measure of whatever this object is going to be 0. And this is actually a theorem from probability theory. It's most often seen there. And what it says is the following. Let's take some x in lim sup of AK. Right? So what is this? This means that for all k, and there exists a j greater than or equal to k, right? So I'm reading from left to right here. So for all k, it's an intersection. And then I take a union, so that means there exists from j goes from k to infinity. X is going to be in some ak. It's going to be in some aj, right? So what this means is no matter how you think of it about it for big K, so for very, very large K, no matter how large of a K I take, I can always find one larger than that K such that I'm in the set. So I'm somehow infinitely often in this collection of sets AJ. So probabilistically, you say that, okay, this event happens infinitely often. Now, if this event happens infinitely often, but is still summable, which is this condition, right? If I'm summable, then I actually, the probability that this event occurs infinitely often, which is this, is going to be 0, right? And it's a fun that you have all the tools it's a little clever how to prove this thing, but I think you could do it if you understand this proof and this theorem here. Okay, so I'll let you guys think about that. In the last part, let's go through a little bit of how do you, now that we have kind of a good handle on what measures do, how to decompose certain measures and how to look at limits of measures. Okay, so this is probably the only one that's necessary in terms of the exam. But if I have two measures on some set X, I want to ask when they're somehow close to each other or they're disjoint from each other in some regard. So the first condition is called being singular, right? So we say mu is singular with respect to nu, and it's written like this, mu perp nu. If there exists a measurable set Z such that when I take the measure of Z and I take the new measure of the complement of Z, I'm 0. So in some respects, if you're looking at it from the perspective of nu, so nu perspective, what I'm doing is I'm hiding all of my, I think about it like this. I'm hiding all of my, the mass. So mass of mu is hidden in the set Z, right? Sorry, the mass, so this is from the mu perspective. So from mu, what I'm looking at is I know mu of this Z is 0. So each of the collection of all of these points is 0. So this is my Z. And so the mass of, and this should be nu now. So the mass of nu is somehow hidden in these points. Okay, and there's like a dual notion, which is somehow the opposite, saying I don't hide any mass. So we say mu is absolutely continuous with respect to nu, and it's written very conveniently like this. If for every measurable set A, I have that if nu of A is 0, then mu of A is 0. So the way I think about it is if I like look at this thing, just symbolically, and I plug in some set of measure A. That's what I think about it like. Okay. Just so we're clear that everybody understands what this is, if for example, nu is Lebesgue measure, can anybody construct a mu, which is singular with respect to this?
Yeah, just take some single point and let the measure of a set be 1 if it contains the point and 0 otherwise.
Yeah, so that's what's called a, so if I let mu equal what they call a Dirac at the point X, what this means is you give me any set that's measurable. Let's say it's like, yeah, some measurable set. And I just check, is X in that set? And I assign 1 to it if it is, and 0 if it's not. Then I know that the measure of points with respect to the Lebesgue measure, right? You can think about it like you give me a point, I can cover it by an arbitrarily small interval, right? And so when I take the infimum over all coverings, I get 0. So I know that points have measure 0 with respect to the Lebesgue measure. And mu, all it does is assign mass to 1 point. So they're singular with respect to each other. Okay. What about for absolute continuity? Can anybody construct something if I have nu is the Lebesgue measure still?
Take any function and integrate it over
Yes.
the set you're trying to measure.
Yeah. So if I take, for example, yeah, let's just do that. If I define mu of some set E as being f of x dx over the set E, what conditions do I need on f if I'm to make this a measure? If I'm to construct this thing. Well, one thing we need is measures are positive. I'm looking at positive measures. So f needs to be positive, right? And what do I need for it in order to be absolutely continuous with respect to the Lebesgue measure? So this dx. If f of x is just positive infinity at all times, mu of e is just the function which assigns everything infinite mass, right? So I can't pick anything.
I mean, I think you actually can pick anything.
It wouldn't be
as long as it's measurable.
wouldn't
Because
be particular though. So for example, if I had, I'm trying to say that mu is this to construct something that does this. For example, if I take, so I take a measure 0 set here with respect to the Lebesgue measure, right? And I integrate positive infinity over this set, right? I think actually, let's see.
it would still be 0. If
You actually still get 0. Yeah. So actually all we need is this.
Well, and f measurable.
And f measurable. F measurable. Let's double check that. So if I define this, just a positive measurable function, this is kind of jumping ahead of ourselves, but if I have the measure, so the integral of this dx equals 0, then this guy actually equals 0, right? Because I'm integrating something infinite. So in general, what it is infinity times 0 equals 0 in real analysis. So this is just convention. Okay. So this is actually an example of what's called a Radon-Nikodym derivative, which is just a fancy name of saying what f is. Okay, and these are just extra. You can read about them if you want. There's a thing called the Jordan decomposition, which says, okay, there's a concept of a signed measure. So things which take values from negative infinity to infinity, inclusive. And what it says is, okay, as long as I can assign a notion of what a signed measure is, I can actually just decompose it as the difference of two positive measures. So somehow in proofs, you can just work with positive measures a lot of the time. Another nice decomposition, which is related, is called the Hahn decomposition, which says that if you give me a signed measure, so it assigns positive mass to some regions and negative mass to others, then I can split it into a part where it's positive, so it's the set P, where E is positive, and then a set N where E is negative, or mu of E is negative. So I can split positive and negative parts. And they're actually gonna coincide with these mu plus and mu minus above. Okay. The next thing is if you give me two signed sigma finite measures, so sigma finite means I can write my space as a countable union of finite measure things, right? So sigma just means countable. Then there exists a unique signed measure, mu perp, and mu with this less than or equal to on X, that are that decompose mu into a singular part with respect to this other reference measure and an absolutely continuous part. Okay, this is what's called the Lebesgue decomposition. Finally, this is what we wrote above. This is called red and Nikodym. If I have two measures and one of them is absolutely continuous with respect to the other, then there exists a unique measurable function, which is integrable, such that this happens, right? And in general, I would like you to think of this as the constraint somehow. I have to be integrable. The function has to be integrable in order to make this association for this theorem anyway. Okay, and then we call f as has a special name. So it's going to be d mu d nu, where these are measures, d nu, integral e u of e. And the way I like to think about this is, it's like the Leibniz rule, right? So if I do this, then I get this. It's just going to be e d mu. That's just good notation.
Do we need integrability even if like the measure mu is infinite but still sigma finite?
The measure mu, I'm not sure. Yeah.
Like if the measure mu on all the whole X is infinite, but
yes,
the measure is sigma finite mu, then the integral left d nu should be like infinite, right?
Yes. So yeah, the sigma finite condition basically says, okay, usually the way these things work is it should make sense for a finite measure, right? If both mu and nu are finite measure. Yeah. The sigma finite condition basically says, so sigma finite it tells me in a really particular way how I can patch from something which is finite measure to an infinite measure space. So finite says that X can be written as you can pick an increasing union without loss of generality of some sets, let's call them xk, where mu of xk, so let's say mu is sigma finite, is finite, right? So for example, R is sigma finite.
But then is f in the theorem still integrable? If mu of x is infinity.
So let me see. So if mu of the whole space is infinity, then this guy,
because I remember that f should be integrable if mu and nu are both finite.
Yeah. Yeah, so in general, I guess I should just say, I should fix this. That's a good point. Let's remove this condition. Whoops. Whoa. This condition, remove. No, let's not remove it. Let's just say this.
Like make it finite?
Let's just make it finite. I think that would be way easier. This is like a way detailed thing, so let's just make it finite. Okay. So let's just say I have two finite measures, then I can decompose one with respect to the other. And there's a version which works there's always a more general version of red and Nikodym, but you kind of get lost if you add too many adjectives. Okay, in the last couple minutes we have, I'd like to talk a little bit about what are called weak limits. Okay, so so basically I've been studying properties of one measure or two measures. But let's say I want to take limits of measures. So the natural notion of a limit of measures is what's called a weak limit. So let's just read through what the definition is. If I have mu n, collection of measures, and a mu, which is a measure, and they're all finite on some metric space X, then I say that mu n weakly converges to mu, and I write it with this hookup left arrow or right arrow. If for every bounded and continuous function phi, which I view as kind of like a test function, when I integrate against phi, my measure, I take I limit towards the correct thing, right? So this mu n converges to mu, right? And so this is just a really nice notion to have. If you know a little bit of functional analysis, the reason we call it a weak limit is the space of probability measures on some finite measure space X, and some metric space X is isometrically identified with, is it a metric? Yeah, it's a metric. Continuous bounded functions on X, and I take the dual of it. So if you know some functional analysis, that's why I call it a weak limit. It's because there is a notion of weak limit here, and it restricts, it gives you a notion of limit there. Okay, I think that's it. Any questions about what we talked about today?
I have one.
Yes.
So if I understand correctly, we start with an outer measure usually, and then we take the sigma algebra from Kara-Theodori theorem as like the natural sigma algebra related to that outer measure. So
yes.
And I was wondering if there is a natural topology like in on R. We can also consider the Borel sigma algebra, like the smallest sigma algebra generated by the open sets.
Yes.
And I was wondering, how is the Kara-Theodori sigma algebra related to the Borel sigma algebra? Because I remember reading that it's larger, strictly larger. But my question exactly was, is it maybe the same as the Borel sigma algebra augmented with the null sets, something like that?
Yeah, generally, so you'll run into this. So that, let me just write down the question because that's a good question. Consider. So this is the B of, let's just work on R. So this is the Borel sigma algebra. So what this is, just in words, is it's the smallest sigma algebra which contains all open sets. Okay, so if I look at this and F, which is going to be the Lebesgue measurable sets in R. Sets. Yeah. Okay, then in general, so I won't just say in general, it's true that the Borel sigma algebra is somehow smaller than F. There are things in here. So there's things that are measure 0. So the Lebesgue measure of this guy, L1 of some set. Let's call it Z. So there exists a Z such that this guy is 0, but Z is not in BR. So you're right about that. Other than that, I don't really know.
Yeah, well, based on what you said, we can approximate a Lebesgue measurable set from above by open sets. So basically we can take like a countable intersection of these approximations and then subtract a null set, and then we get a Lebesgue, any Lebesgue measurable set. So I think you're right that it's generated by null sets and the Borel sigma algebra.
Okay. Yeah, it would be interesting to see that just as like a fun little thing in math. This is what's related to what's called the Borel hierarchy. And notions in set theory and logic. So if you go, you can fly pretty close to the sun here, and if you ask questions in that direction, you start going into logic. And in general, just as another remark, this construction, in some sense, you can view it. I view it in this way is like, okay, Lebesgue measurable sets, I'm somehow completing it with respect to measure zero sets. So in general, if I look at Brownian filtrations, this is outside the scope of the class, but often require a null set closure condition to make certain theorems work. Just in case you're interested in probability. Okay, that was a good question. I think I have time for one more. Okay, if there's no more, if you guys are bored, I have a bunch of problems I'm about to upload. And the way I'd like you to do is maybe work on a few from this measure theory section, right? And so these are coming from past exams at UT, and I've just organized them based on problems. Some of them are fun. For example, this one's kind of fun. Number 4 is one I might recommend. And if you want, you can show the Lebesgue measurability theorem if you want. But yeah, pick a couple. If you can't, spend maybe 30 minutes max on each one of these. If you can't get it, send me an email or reach out to me, and then we can talk about it during the next lecture. Okay, well, I'm going to stop recording. Stop share.